So here's a summary of topics for numerical exam analysis exam 2. As we teach the course, at least, we've done our course. What topics have we done since exam 1? The first topic we did was just talking about polynomials. Ultimately, to emphasize the synthetic division is useful for applying Newton's method. Do you remember that? Using synthetic division, we called it Horner's algorithm. Synthetic division to apply Newton's method to polynomial equations. Okay, we also talked in general about polynomials, how, for example, there's the fundamental theorem of algebra saying every polynomial's got at least one complex root. And in fact, there's a corollary of that says if degree n, it's got exactly n complex roots if you count multiplicity. Probably won't test you on that, but that is something every math major should know. The fundamental theorem of algebra. Just as a reminder of how this goes, of course, Newton's method. I don't remember if we started with Pn plus 1. Gives Pn in terms of Pn minus 1. In general, with this kind of recursive equation, f doesn't have to be a polynomial to use this. But if you're going to use it with synthetic division, then f has to be a polynomial. So what does the synthetic division do? It helps you evaluate these values. When you set up your synthetic division, you're plugging Pn minus 1 into f initially, so you put the coefficients of f here, the polynomial f. Whatever the final remainder term is, that is f of Pn minus 1. And then it turns out if you do synthetic division again, and this was kind of magical, whatever the remainder you get for that one is f prime of Pn minus 1. You have to prove that, but it's not completely obvious. But that's the way it turns out to be. So doing that twice gives you these values to allow you to do one iteration of Newton's method. And probably for the test, if I put this on the test, it would probably be one iteration would be good enough showing your work this way. By the way, this was not on the old exams from 2018. This kind of thing, I didn't really emphasize that in 2018. I just emphasized synthetic division itself, and I don't think I tested them on it, but we did spend a little bit more time than I did back then. All right, so applying synthetic division to do Newton's method is the main thing that we did there. Then we got into chapter 3. So there's the Lagrange interpolating polynomials. Chapter 3 overall is about interpolation. So we just reviewed that 10 minutes ago. You've got nodes x0, x1, x2 through xn. So there's n plus 1 nodes, giving you in general a degree n polynomial, though it's possible by chance that it could be less than degree n. For example, if all the data points, including the y coordinates, gave you points that lied exactly on a straight line, even if n were 1,000,000, the polynomial in the end would be linear. A bunch of stuff would cancel. But in general, it's going to be nth degree, and you could write it as a summation. K goes from 0 to n of function values times the basic interpolating polynomials, Lk of x, where Lk of x is 0. There's 1 at the kth node and 0 at every other node. So let's see, you could write its formula in this kind of way. You'd want to emphasize that x minus xk would be missing. You have an x minus xk minus 1 and an x minus xk plus 1. In the numerator, and the denominator would be the same things, except you replace all the x's by xk's. So, I mean, this is kind of a pain to write out like I'm doing here, but it's important to understand the idea here. And again, the benefit of this, especially when n is bigger than 2, is that it allows you to find the nth degree Lagrange interpolating polynomial formula without bothering to solve a system of, if n were 10, you wouldn't have to bother solving a system of 10 equations and 10 unknowns with linear algebra, which would be very computationally intensive even for a computer. Theoretically, you could do it by hand, although it still would be a pain, but less painful than linear algebra. When n is 0, 1, or 2, you might argue maybe the linear algebra is easier, but certainly if n is bigger than 2, this is probably better. From that, we went on to Neville's method. The idea being you got a tabular form for the data. You've got your i's, you've got your xi's. And again, maybe you don't make the I column in case it causes you to make a mistake. Maybe you want to make a column for x minus xi. Oops. That's an xm. And then you've got your p's or your q's, depending on how you want to do your labeling. The next column is going to be 0th. I always remember it this way. This is going to be 0th degree approximations, constant functions, the values of the function f at the nodes. In each case, you are effectively just using one node. You can label it p sub I. Q sub I comma 0 is just f at the nodes. F of x0, f of x1, f of x2. These are constants. F of xn. So if you watch the extra video, those are 0th degree things as functions. They're constant functions whose graphs are horizontal lines. And in any situation, and as you make Neville's method tables, any one of these numbers could be thought of as an approximation to f of x, where x is some fixed number between x0 and xn. The next column, you're using 1st degree approximations, so you're using 2 nodes. And you start in not the 0th row, but the 1st row. So the labeling of the subscript should be p sub I minus 1 comma I, or q sub I comma 1. And that's where you start using the formula for Neville's method, which right in this spot is going to be this number times this number minus, remember to do the minus, the product of this number with this number, divided by the difference this minus that. Okay, if I don't write it out. On a spreadsheet, you then copy and paste that down. Those are all first degree approximations, numerical values to approximate f of x. Depending on where x is between x0 and xn, some are better than others. X, for example, is close to xn. The ones at the bottom are probably a better approximation than the ones at the top. Next column is going to be second degree quadratic approximations, starting right here. The labeling would be pi minus 2, I minus 1, I, or qi2. And for this one, always start up here, do that times that minus this times this, all divided by this minus that. And then copy and paste down. And then similar for the other ones. Good. Third degree, then fourth degree. Then ultimately, at the end, you get a number in the lower right corner. That's for the nth degree, and should be, though not guaranteed to be, the best approximation for f of x. So you're really using a bunch of Lagrange interpolating polynomials in a recursive way to hopefully get a best approximation in the end. Divided differences, the next topic. You've got what you might call the Newton expansion of your polynomial approximation. By the way, these polynomial approximations are, I haven't emphasized this, but they're all based on something called the Weierstrass approximation theorem, which guarantees that continuous functions, even if they're really wild, which they can be, there are plenty of really wild continuous functions, can be approximated arbitrarily well by polynomials, though the degree could be really, really, really high if the function is really, really wild. But you end up writing Pn of x as f of x0 with square brackets plus a summation. K goes from, let's see, what is this going to be? If you just have a 1 number in there, it's called a 0th divided difference. The next term you'd want to call a first divided difference, where you'd have a x0 and an x1 in there. You could say, if we go through xk, that k should start at 1 here and go up to n minus 1 or n. Oh, I'm forgetting how we label it here. Oh, let's think about it here. And the product is going to be x minus, these are coefficients. The product is going to be x minus x0 and x minus x1. And you want this to be nth degree. There's n plus 1 nodes, but you want it to be nth degree. So you want n products here. We're starting with the 0th subscript. So the last factor has to be x minus x sub k minus 1. K is going to go up to n here. And I think, let's see, because of that, I think we do have a k there. Because the last one is going to be when k is n, and that'll be an nth divided difference. Starting with the 0th divided difference going through n. Yeah, that is correct. Where, yeah, these things are all divided differences. It's where you make, on a spreadsheet, you make your triangular shape thing. F of x0 is just notation for function value at x0. That's a 0th divided difference. F square bracket x0, x1 is a true divided difference of function values. You could also call it a difference quotient, but here it's traditional to call it divided differences. It's most natural to have the x's in order from least to greatest, but they don't have to be. And this does give you the same thing, even if you wrote it this way. So that's a first divided difference. The second divided difference that you use is this. It's iterative in nature. So this is the way it would be here. Etc. That pattern would continue. In your spreadsheet table, let's just make the xi column here. So you'd have your zeroth DDs here. Those are just function values, but I'll use divided difference notation. Of course, when you do this on a spreadsheet, you want to make the spaces between the rows as well. The ease of copying and pasting with space in spreadsheet. Then your first divided differences. Okay, I'll try to make it as if I'm doing the spacing in the spreadsheet here. Etc. Second divided difference, etc. And again, the idea is it's the numbers on the main diagonal from the upper left to the middle right that are the ones that give you the coefficients you want. But you need the other numbers in the table to compute all of it. From this, we also get Newton's forward and backwards difference formulas. For sake of time, let's just look at them in the book. With Newton's forward difference formulas, you do want x0 through xn to be in order from least to greatest. And you also want them to be equally spaced nodes, distance h apart. That allows you to write this formula in other ways. It's the same formula, you're just writing it in other ways. One way to write it is like this. So what's happened there is the divided differences, let's see, or no, these products are what the differences x minus x0 and x minus x1 and x minus x2, etc. become, where you've written x in this form as x0 plus sh. To use it, you do have to figure out what s is based on a given value of h. H being, again, the successive distance between the nodes. You've got to figure out what s is, solve for s, and then you can use this formula. You should be able to use this formula in this form, even though it's not a numbered formula. Maybe you want to circle it in your book, write it down in your note card. Another form of the formula is this one. Should also be able to use that. Compute these binomial coefficients necessary. This is not the most pleasant formula to use, but in theory, you should be able to use it. If I did have to use it, probably n would be small. Maybe with any of these in the in-class portion, at least, n would be fairly small. 2, maybe, just to get practice showing me you can use the formula and show your work. And then they derive it in terms of the forward difference operator to ultimately write it like this. Delta to the k power of f of x0 is the forward difference operator applied k times to f of x0, meaning you make another table. Function values, the first column, then you do apply the forward difference operator. Just do differences. Make the next column, and then the next column, and then the next column. And since you're applying it to f of x0, you just use the numbers across the top. That's all you really need. But to get the very last number in the top right, you do need all the numbers each time. You do need to multiply those by binomial coefficients to be able to use this. Backwards differences, you're using the numbers in the opposite order from xn to x0. And the h becomes negative. You're writing x in terms of xn, s, and h. H becomes negative, the negative distance between the nodes. S is still positive. You should still be able to solve this for S. You may want to circle this formula. And then you can also write it in terms of the backwards difference operator, ultimately, to be able to do it this way too. If it was in part of the in-class exam, be a fairly small value then to show me your work by hand. Part of the take-home, be something you do in a spreadsheet. We skip center differences, which I'm sure you were happy about if you tried to study that. And went on to Hermite interpolation then. And yeah, we had all this theory involving these crazy formulas here, but the ultimate thing that we did, though we didn't spend much time on it, is said you can do it with divided differences. Conceptually, we're trying to match up not only function values, but derivative values. If n is 2, for example, so you got 3 nodes, function values and derivative values at those nodes, the degree of the Hermite polynomial that you get is 2n plus 1. 2 times 2 plus 1 would be 5. You need a 5th degree polynomial to match both function values and derivative values. It's a little tricky with the table because in the first divided difference column, you need derivative values every other spot. But you still use the numbers on the upper left to middle right diagonal to give you coefficients of the interpolating polynomial right here. The z's include repeats. You know, it's a very quick summary of the Hermite interpolation, but we're almost out of time here. And then there's the cubic splines. We didn't do everything. With fairly simple examples, relatively simple, we focused on the basic cubic splines, either with natural or clamp boundaries. I know we did it fairly quickly in class, but if you think about fairly simple examples, it should make sense. And you should be able to write down your equations for the in-class exam to solve, but not necessarily solve them for the unknown coefficients of your piecewise defined function, where each piece is a cubic function. Not solve that system for the in-class exam. For the take-home, you should be able to solve it. You wouldn't necessarily, and with Mathematica, you wouldn't necessarily have to do what I did in class with the subscripts. But you should ultimately be able to use the solve command for a system of linear equations, maybe with 8 equations and 8 unknowns. And get those conditions right. Don't make mistakes like I did to get a solution. And again, the final answer is a piecewise function with each piece being a cubic written in certain forms. And you should be able to write that down for the take-home if I gave you that. And then this little bit of we've learned about numerical differentiation today. Okay. I haven't assigned any problems on it, but an example similar to what we did, probably not the full thing because it would be too time consuming. But like, you know, what we did today, you know, maybe I give you a table like this and maybe I'd partially fill in values of the derivative and you'd have to fill in a couple other ones, maybe at one midpoint one and one endpoint one. So you should know both formulas, the midpoint formula and the endpoint one. The midpoint one's easier, more intuitive. Okay, I hope that was helpful to try to recall everything. Have a good day.